All right, you guys, just a quick little presentation on earthquakes. Maybe. Here we go. All right, so definitely know the definition of an earthquake. I think we should be okay at this point with all your reading and study guides, etc. But always know the basic definitions. It's the energy released in the form of seismic waves, and it's released from the position between two rock masses, faults. And you can't see all the hand motions that I'm doing, so I probably shouldn't bother. Anyways, know what a fault is, and if we remember back to previously, as we talked about, it's a break between two rock masses where there's movement occurring, and where that movement occurs is where the earthquake is. So if you remember back to earth science, your elastic rebound hypothesis or elastic rebound theory is the storing of energy that's released abruptly. So remember when we were in structure, we differentiated between stress and strain. And so what we have is, think of two cheese graters, I think is the analogy they use in your book. And if we flipped them opposite one another and tried to move them, there's a lot of friction, all those teeth in the cheese grater, and they get hung up and they don't want to move. But if we continue to try to move them, there's a lot of energy that's building up, right? And if we continue to pull on those or try to slide them across one another, eventually probably some of those teeth in the cheese grater are going to break or give or bend, and there's going to be that sudden movement and release of energy. Think of rubber bands. As we pull rubber bands apart, there's a lot of potential energy in there, right? And eventually, when that rubber band breaks, it's going to release that energy very quickly and snap you back in the hand. So that's some. Hopefully that helps with elastic rebound theory. A couple parts of where an earthquake takes place, or locations that you should know. The focus, or sometimes referred to as a hypocenter, is where the initial breakage and movement along the fault actually occurs. So when we're talking the focus, we're talking generally underground along that fault where the actual movement is taking place. If we go directly above the focus, straight above to the surface of the earth, that's the epicenter. So when you hear on the news they talk about an epicenter, that's where you could drive to that location and stand on top of where the earthquake happened, which would be underneath the ground at the focus. All right, so know the difference between those. They're easy to mix up. Focus is where it actually happens. Epicenter is at the surface of the earth, directly above it. There's two main types of seismic waves that we're going to be concerned about: body waves and surface waves. Body waves travel outward from the focus in all directions through Earth's interior, and just as it sounds, surface waves travel on the Earth's surface away from the epicenter. So you can see these are all of the body waves radiating out, and then along the surface here, we would have the surface waves. So there's a couple different types of body waves. There's P waves and S waves. P waves, primary waves. They're compressional or longitudinal body waves in which the rock vibrates back and forth parallel to the direction of movement. These are the fastest. They go from 4 to 7 kilometers per second. And this is the first one that arrives at the recording station. And something very important to understand and know as we talk about mapping the Earth's interior is that these waves go through solids and fluids. Important to remember, because an S wave only goes through solids, not through fluids. And so an easy way to remember that is S, even though it's a secondary wave or shearing wave, it also only goes through solids, S and S. So anyways, an S wave is a shearing or a transverse wave, and so it's moving perpendicular to motion, or the propagation of that wave. They're a little bit slower at 2 to 5 kilometers per second. And this is, again, the secondary wave to arrive at the recording station. And they pass through solids. So remember that. In your book, you have these diagrams, and if you could envision a slinky and laying it on the ground and just kind of pushing it, and you have the bunched up coils moving through the slinky. And that's an example of a primary wave. Okay, the direction of movement is parallel to my brain's not working right now, to the propagation where it's going. So same direction. Down here for the secondary wave, if sometimes you take a rope or a hose and you get that kind of standing wave going on, the motion is perpendicular to the direction of travel. So this wave is traveling this way, but it's moving up and down, so perpendicular. These are the same way. Hopefully that makes sense and I didn't confuse you more. Anyways, surface waves are the slowest type. They're going to arrive at your seismograph behind your primary and secondary waves. There's two different types. Your Love waves, which have a side-to-side motion along the ground surface, and they cannot travel through fluids. And then Rayleigh waves move in more of an elliptical path, opposite the direction of their wave of motion. So they're kind of, if the motion or direction of travel is this way, they're moving in this elliptical opposite. So in this instance, it'd be counterclockwise. And these are the ones that are very destructive to buildings because of that kind of rolling action that takes place. Pause for a second. Okay, the way that we locate and measure earthquakes, we use different tools. We have a seismometer, and that's used to measure the seismic waves. And the seismograph is the actual device used to produce that permanent record of the seismometer. And then a seismogram is the permanent paper that records the vibrations. Or now it's digital on a computer. But think of a telegram. Back in the old days, you'd order a telegram and someone would bring you a note to your door. Seismogram is that note with the information for your seismogram. So down below here, you can kind of see how they work. You've got this heavy weight on the spring with a recording device, and then you have this piece of paper. And as the ground moves up and down, this moves, and in relationship, it's able to record the information on the seismogram. So the weight's staying in place. Everything else around it is what's moving, as you can see right here. So hopefully that kind of helps you visualize what's going on. Okay, and then so you guys in your lab have had practice determining the location of the earthquake using the time travel curve. They're different. This one's a little bit different than in your lab manual, but they all kind of work the same way. You've got your primary wave down here, and you have your S wave up here. And when you calculate the difference in time between your P and S wave, you have a certain amount of time. So for instance, this particular seismogram picked up that there was an 8-minute interval in between the arrival of the P and S wave. And so we can use this travel time curve to figure out that, oh, okay, well, it was 5,200 kilometers away. And then we can plot the radius coming out from that epicenter. This is a very, very basic kind of rudimentary way to calculate epicenter. It's not really the way that it's done, but it'll help you visualize what's going on. Okay, so your P and S waves leave the earthquake, your focus at the same time, and obviously they arrive at different times, and so that's how we're able to calculate that time interval or lag between the P and S wave. So once we've done that and we know that the distances away from each of the epicenters, then we can use that information, plot circles, and triangulate and figure out where that epicenter is located. Again, this is very, very basic and kind of, toned out a bit, I guess. We're working on a flat map, and the surface of the Earth certainly isn't flat. So there's a lot of other variables that need to go into calculating the epicenter that we're not doing here, but this gives you kind of an idea of what's going on. It's also not going to really calculate our depth, right? So the depth of focus beneath yours can also be determined using triangulation, though. All right, I think, and so the minimum stations that we need on a map is 3. Obviously, the more that we have, the more precise our epicenter is going to be. When there's an earthquake, we're getting information or data from thousands of seismographs from all over the world, especially on those big earthquakes. All right, so I'm going to go ahead and I think stop it right there, and I will continue on part 2 here in just a little bit.